Everybody, we are discussing memory. In the last class we looked at static RAM. In today's class we shall look at dynamic RAM, and after that we shall discuss how memory expansion is possible by using multiple memory blocks. Okay. So, we will start from DRAM dynamic RAM basics, okay. And since the number of memory cell that can be put into a DRAM memory unit is quite large, the packing density is higher. So, the number of address line will be a bit more, for which to save pins we can utilize multiplexed addressing, that part we shall see. Then we shall look at memory cell by 4 transistor, 3 transistor and 1 transistor, and at the end we shall look at address and data range expansion. Right. So, what we use in design of dynamic RAM based memory cell is that the MOSFET by nature has infinite input impedance, that we all know, okay, because it is a field effect device, it is not a current control device like BJT, right. So, the leakage current at the gate is very small. So, the parasitic capacitance that would be there at the gate of the MOSFET, that can be used to store charge for a short time. Of course, there will be small leakage, okay, but for a short time it can be stored, and that can be used for storing binary information. Okay. So, this capacitance acts as a memory cell, and this provides us a simple circuit, right, and a higher packing density. Number of parts required becomes less, okay, and the cost also per unit memory cell becomes much smaller. So, this is the strength of this approach. Of course, as we see in any design, there is always a trade off. The trade off is that what we just noted, that the capacitance, though the leakage is these can be is relatively small, but still it leaks. Okay. So, it requires periodic refreshing, otherwise the sanity of the data that is there will not be properly understood, whether it is a 1 or a 0, okay, because the level will become similar. Okay. So, that is one particular thing, and this is called refreshing of cells. Okay. So, periodically of the order of millisecond it need to be refreshed, okay, even when memory read or write operation is not taking place. Okay. So, that the previous value whatever it is, it remains stored. Okay. This is one specific characteristics of DRAM, okay, which was not there in SRAM, for which the memory cycles that are there, the timing cycles for memory read write operation becomes little bit different, okay, I mean somewhat complicated compared to SRAM. Okay. Now, as I was telling that it can pack a large number of memory units, memory cells in one particular block, okay, because of the simple nature of the circuit. So, you can expect that for a particular memory cell, the number of address pins will be quite large, okay, because it is whatever the number of memory cell, log of that to the base 2 is the number of address pins, address bits, address lines that will be required. So, when it becomes higher, okay, then the number of pins required to access the memory also becomes larger. Okay. Now, these additional pins that requires higher cost. Okay. So, for which the concept that we can use in some such devices is the multiplexing of address lines. Okay. So, here you can see one such example where we are trying to address 16K into 1, okay, that kind of memory block. So, this is that kind of memory block, right. So, 16K means you need 14 address pins, 14 address lines, 14 bit address. Okay. So, in this arrangement what you can see that A0 to A6, the 7, okay, and A7 to A13, there is a stroke over there, both are fed through same set of 7 pins. Okay, we do not have separate 14 address pins, we have only one common set of 7 address pins by which both A0 to A6 and A7 to A13 are sent. Okay. So, when you send A0 to A6, right. So, if you consider them as a row address, so this particular row address select, this particular stroke, okay, is exercised and that is latched into this particular register. Okay. And then when you are sending A7 to A13, so this one will be at a different point of time, of course. So, this column address select, this particular input to this column address latch, that will be stored and it will store that information. So, this is going to row address decoder and this is going to column address decoder, and we have already noted the memory based addressing scheme, matrix based addressing scheme before. So, this is the row address that will come, okay, and this is the column address that will come, and at the cross point there is the memory cell. Okay. So, what is happening now because of this, that we are able to save 7 such pins, but the address bits are made available at different point of time. So, this is the multiplexing aspect of it. Okay. So, whenever the number of such pins requirement becomes high because of higher packing density, we can think of some such way of addressing, which is also known as multiplex addressing. Clear? Now, we look at one DRAM memory cell which is 4 transistor base. It is somewhat similar to what we had seen in case of 6 transistor base MOS based SRAM cell in the last class. Okay. So, there is some differences that we shall also tell. So, first of all, so this is the basic memory cell, whatever you see over here. Okay. So, this is the basic memory cell. In SRAM based memories, SRAM using MOS, what we had after this, we had a NMOS load connected to VDD. Okay. So, this was always connected, and the transistors, these opposite transistors were acting as inverter, and the memory cell was basically made up of these 6 transistor put together, right. So, in this case, it is those load transistors are not there holding the cross coupled inverter in one particular state value. Rather, the capacitances that are there, which can store charges for a short time, they are used in this particular case. Of course, as we have noted, even when the memory is not read or written into, so it need to be refreshed, for which a separate refresh lines are associated. Okay. So, let us see how it works, right. So, the first of all, these parasitic capacitances C1 and C2, they are used for storing of information. To start with, we consider that Q1 on, so this is the Q1 on is storage of 1, okay, and Q1 on, Q2 off, and Q2 that is storage of 1, and Q1 off and Q2 on is storage of 0. So, that is the nomenclature, that is what we are following. Okay. And that time C1 is, this C1 is charged to VDD by some mechanism. So, these data lines or all those things that we shall see during the writing process, how it happens. So, this is charged to VDD, okay, this is on, and at that time this is charged to a low value, okay, low value. Okay. So, that will be the case because this is on, means this is a low resistance path, right. So, C2 will be having a almost near about 0 volt. Is it okay? So, this is VDD and this is, because this is on. So, there is a path that is available. Okay. So, if not accessed means this X is low, Y is also low. So, that means this is isolated from the rest of the circuit. So, it will maintain this value, okay, if these capacitances are not leaking. So, C1 it will maintain its value, C2 will maintain its value. This is at VDD and this is at 0 volt. Okay. But as we have noted that it C1 charge which is charged up to VDD, it will gradually leak and it will come closer to the C2 value, then the information will be lost. Okay. So, before it loses significantly, whatever charge it has there with it, okay, we need refreshing. Is it fine? And for refreshing, then what we do? We need to recharge the capacitor, okay, and for which what we consider here, this X we make high, right, and this refresh R input we make high, right. So, at that time what is happening? So, this is high, this is high, this is high. So, this is on, this is on, this is on, this is on. Okay. These transistors are providing path to this VDD. Okay. So, what will happen? So, this VDD will get the path over here to charge the C1. Is it all right? Okay. Because Q2 is off. Because Q2 is off, so the path available over here is this. Is it fine? And at that time what will happen? What about this path? So, VDD, there is a path over here, but this particular path, this Q1 is on, right. So, it will go through this low resistance path over here, and for which the C2 will remain at low voltage only. Is it okay? Because it is getting bypassed when this is on. So, before it appreciably falls, we need to do this refreshing. Is it all right? So, all the rows, all the cells in a particular row, okay, to which X is connected, so they get refreshed together, okay, by this particular line. So, this is the refreshing act that is happening at a periodic interval, okay, even when read or write operations are not taking place. Fine. Next, let us see how the write and read operation takes place in this particular cell, right. Refresh we have understood. So, what we see, this is the the control block. This control block is similar to what is there in the NMOS based SRAM that we discussed in the last class. Okay. This particular block is similar. Okay. This block is different. Okay. The control logic part remains as it was for SRAM, okay, which we did not discuss in that detail, but we can apply this particular block there also and understand how it works, right. So, coming back, so for the write operation, this block and this block comes into picture, right. So, at that time of course, this cell need to be accessed. So, X is high, so row address select and Y is high. So, for which this transistor is on and this transistor is on, this transistor is on and this transistor is on. Is it okay? Right. So, now this is the data and this data bar line, right. So, this gets a path, this gets a path from here through it because these transistors are on, okay, like this, right, to come here. Similarly, this address gets a path over here, okay, sorry, like this to come here up to this point. Is it clear? So, in the write operation, so this particular one is high, so this is on, so this is on, right. So, if D in is low, right, so if this is low, then this transistor will be off. So, I put a cross mark means off, and then D in bar will be high, okay. So, this will be on. So, at that time what happens if this is off, okay. So, this is the transistor is used as a load. So, this will be high, right, and this will be, this one is on means there is a path available, this is also on, this Q17 is also on. So, this will be low, right. So, at that time you are forcing from external this through this data line, okay, a high over here and a low over there. Okay. So, what would happen because of this, right? So, this high and this is low. So, this C1, okay, will become low because this is low and this is high. So, that will charge C2 to high. Is it clear? Right? It is being forced externally through the data lines. So, that is what is happening, right? And whatever charge C1 has, now C2 has become high. So, Q2 is now becoming on, right? So, it will get discharged through this, right, through this. Is it clear? Right. So, that way earlier Q1 was on, the consideration that we had with which we had started the discussion. Now, this Q1 becomes off and Q2 becomes on. So, earlier we considered Q1 on means a storage of 1, now Q1 become off. So, it is now storage of 0. Okay. So, whatever data D in that was low, right. So, low that has been communicated, that has been included now in the memory cell. Is it fine? So, this is the way data. So, similar thing, this is symmetric in nature. If D in is high, similar thing will happen for the other side, from the other side. So, this side will be high and this side will be low, corresponding transistors will be on or off, and the data writing will take place accordingly. Clear? Now, what happens to read operation? So, during read operation, this input will be low, okay. This is low, okay. So, this is off, right. So, if this is off means this does not get a path in this direction, right. So, and also this D input is not in consideration, right. So, at that time your, of course, this is accessed, this is accessed. So, this is on, okay. This Y is high and X is high. So, this is on and this is also on, these two are also on, okay. So, this is the cell being addressed, okay. Now, if the C2 is low, so C2 is low, okay. So, C2 is low, that means C1 is high, okay. So, Q1 is on, okay. So, what will happen at that time? So, this VG Q3, right. So, this is your Q13. So, this is your 13, okay. This is the read amplifier and this is the 14, this is the another read amplifier, okay. So, at that time what has happened, if this is low, it is low, right. So, this low will come through this, right, and so this is low over here, this is low over here. So, this is the inverter configuration amplifier. So, this will be, D out will be high, right. So, this is high at that time, okay. So, C2 low, that is Q1 on. So, D out you see as high, right, and at that time what will happen to this line? So, C1 is high, right, and Q2 is off. So, this high comes over here, okay. So, this high comes over here through this data line and comes to this point. So, this is high. So, this transistor is on, right, Q14 is on. So, this output is low, okay. So, this is the way data is read from the cell, fine. Now, looking at the other two DRAM cell configuration, memory cell configuration with lower number of parts. So, one is 3 transistor configuration. So, here what you can see that this is the parasitic capacitance between the gate over here and the ground that is there, which is used for storing the information, right. When the C is fully charged, okay. So, this voltage is high. So, this Q2 will be on, right, and then this ground is getting a path over here. So, D out will be low, and if it is low, then it is off and this D out will be, D out bar will be high, okay. So, if just opposite things is available. So, if it is high, this is low, this is low, this is high. So, that is why it is D out bar, that is has been mentioned over here. And for writing, right. So, then this is W is on. Okay. So, at that time this D in, if it is low, so it will be low, and if it is high, then capacitor will be charged to high value. Okay. So, this is the way it works over here. And for one transistor, this is the memory cell. Okay. So, this is a capacitor, this is not the parasitic capacitor we were talking about, this is an external capacitor which is storing the information, this 1 bit information, right. And so, this is the Y address line and this is the X address line. Okay. So, this column line that you see is also data line. Okay. So, which increases packing density further, but there is a catch, we shall see, right. So, when X is high and Y is high, so both of them are high. Okay. So, whatever is the value of the C1 that gets sensed when the read operation is done. Okay. So, this is the way it is sensed. So, if it is low, then it is sensed as low, if it is high, it is sensed as high. There are some more issues we shall now shortly discuss. So, that is the read operation, and the write operation, of course, when both of them are high. So, from this side, okay. So, this is from the right amplifier, the this transistor is on, this transistor is on, right. This C1 gets charged according to low or high value that is coming from the right amplifier. Okay. So, this is the way this memory cell is storing information high or low. Okay. Now, regarding the other issues that are there with this arrangement. Okay. So, here there is a large parasitic capacitance that occurs as C2 over here. Remember, this is column line. So, many such lines will be in parallel, right. Many such cells will be addressed by this particular line. So, many such capacitance, they will be in parallel. So, that will increase the effective capacitance value of it, which is roughly 10 times more than this capacitance value. So, whenever you read it, because of the charge sharing, charge dividing that is happening, this charge coming over here, so it becomes a destructive reading. So, this charge information here it gets lost. So, after every read you need to have a restoration, restoration of whatever previous value was there in this C1. So, this is an additional thing, though the density is more, least number of parts are used. So, this is a one transistor configuration. And the other issue with this one is that for reading it is preferred that you precharge this particular data line, the column line, to high value. So, that means this capacitance etc. is already precharged. Now, after that, whenever this X becomes high, I mean this particular cell is becoming getting accessed, then depending on the value of C1 which is low or high, so there will be small increase or small decrease in this particular value over here in this reading. So, that difference is actually getting sensed. So, this is the other way of reading this particular thing. So, that is also something which we consider in this case, but it provides the maximum density. So, we now move to this memory expansion, and when we talk about memory expansion, there are two possibilities. One is the address range expansion. So, what do we mean by that? So, there is an example. So, this is the number of rows, that number of addresses, number of locations, that is 1024, and each in each address there are 4 bits of binary information is stored. So, 4-bit word is there. So, when we talk about address range expansion, so it remains 4, but now we want 4096, 4K number of memory locations available for the designer. Okay. So, how we can do that? If we have a 4K cross 4 memory, which is fine, you can directly use, but if you have 1K cross 4 like this, right, what you can do to expand the address range, which originally is meant for 1K address, okay, 1K memory locations. So, to do that, one mechanism that you can see over here. So, 1K means 10 address lines will be there, okay, 2 to the power 10 is 1024, okay, and 4K means 12 address lines will be there. So, you take 4 such 1K units. So, this is one unit, 2, 3, 4, okay, and the lower this 10 bits A0 to A9, which is there as address bit inputs to each one of these 4. So, you make it common. So, you connect it to all of them. Okay. So, higher 2 bits A11 and A10, you pass it through a 2 to 4 decoder to generate 4 such lines. So, 0, 0, 0, 1, 1, 0 and 1, 1. Okay. And then that you connect to chip select lines of each one of them, right. So, what does it mean? When 0, 0 is placed here, A11 and A10, right. So, this particular block will be selected and not the other ones. So, if this is 0, 0, if this is 0, 0 and this address A0 to A9 is all 0. So, basically you are accessing the location 0, 0, 0 in hex. Okay. So, all of them are 0, that particular location is accessed. You can read from there or you can write into, okay, depending on what operation you are doing. Okay. So, if you now change this A9 to A0 to 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, okay. So, this 0 becomes a 1. So, it will happen. So, you will be reading from location 0, 0, 1, that is in hex. Okay. From that location you will be reading or writing, right. So, because this is remaining, these two A11 and A10 remaining constant at 0, 0. So, whatever you do with the rest of the A0 to A9 bit, okay, that is happening over here in this particular block. Okay. And how much you can go ahead with this? So, all becoming 1, A0 to A9. So, that is your 3FF. Okay. That is your 3FF that you can read in hex, means group of 4. Okay. So, this address will be available here, right. So, next, if it is 0, 1, so 0, 1, this A11 to A10, so this is what will be considered, right. This decoder output will be considered. So, accordingly this chip will be selected, rest are not selected. Okay. So, when this one is 0, 1 and rest all these A9 to A0 is 0. So, basically you are locating the first address, okay, of this particular memory block. So, that is 400 according to this expanded address range, okay, and last address over will be 7FF. Similarly, this one will be 800 and last address will be BFF and this is C00 and this will be FFF. Is it clear? So, that is the way we can increase the address range. Coming to data range expansion. So, the number of address bits remain same, okay, data bit we want to increase. So, here is an example. So, this is IC 74201 is a 256 cross 1 memory block, memory IC. So, that means 256 addresses are there. In each address location only 1 bit information can be stored, okay, on 1 bit information is there, and we want 256 cross 4. What will we do? Okay, we shall put 4 of them in parallel as you see over here, right, and the address line will make common and we will feed same address line, right. So, whenever now invoke a particular address, so each one of them will be invoked, the first location for each one of them will be addressed, right, and then you can write or read from each one of them, okay, depending on your control inputs, okay, and each one will give you 1 bit of information and together you get 4 bit of information. Yeah, simple. Okay. Now, if you want both address and data range expansion, right, whatever we have learned just now, we shall put them together. So, one such example over here, say 256 cross 1. So, that means that example of 74201, which is 256 cross 1 memory cell, and that is there, and we want a memory which is 1024 cross 8 using it. Okay. Then what we shall do, right? We need to increase the address range, otherwise also increase the data range. So, address range, right. So, which was to start with 256 means 8-bit address was there, and 1024 means 10-bit address will be there. So, for this additional 2 bits we will be having a, so this is a 224 decoder, sorry, okay, will be there 224, right. So, it will be generating 4 addresses the way we had seen before, right, and in each location 201 provides 1 bit of binary information, and we want 8. So, 8 such will be there, D0 to D7, right. So, 4 such rows which is expanding the data address range the way we have configured it, and 8 such columns increasing the data range. So, 4 into 8 32 such memory blocks of IC 74201 will be required to get this one. Is it fine? And this memory block could be any of SRAM, DRAM type, I mean depending on whatever you are using. Okay. So, with this we come to the conclusion of this particular class. What we have seen, that dynamic RAM made from MOSFET stores information in the form of charge, which is available at the gate capacitance, parasitic in nature. Because of the leakage, it requires refreshing to replenish the lost charge. Okay. Larger sized memory we can do better by multiplexed row column addressing, which saves pins, number of pins that would be required for the memory IC. And we had seen how 4 transistor DRAM memory cell, 3 transistor DRAM memory cell, and 1 transistor DRAM memory cell works, okay, and their specific characteristics. And further we have noted that address range and data range of memory can be expanded by using additional units, okay, and decoder for increasing the data range, and also using chip select unit together. Okay. Thank you.